Okay, so we bought these water guns here, and they have a claim saying they could hold 3.72 fluid ounces, and it could go up to a distance of 15 feet. For the volume, we're going to use the density equals mass over volume to check that claim, and the distance we could use a mixture of Bernoulli's equations and some formulas from Physics 1. So let's go. So we're gonna fill this water gun up to test the claim. So we're gonna put this on the scale, and then we're gonna negate that weight so we can just find the mass of the liquid. Now we're gonna pour it. And it is 118 grams.
Because Jake didn't do math, basic physics math, I'm here to show you how to do it. So we have the formula, density equals mass divided by volume. Now we're going to test the claim of their volume since they claimed it to be, I think it was 2.72 fluid ounces. We're going to test to see if their claim is correct. So we know our mass is equal to 118 grams. Since we're in grams, we're going to use the density of water. The density of water would be 1 gram over a milliliter. Milliliter?
Cubed.
No, it's just milliliter normal. There's no cubed. And equals to 118 grams over volume. Now we're going to solve for V, so we're going to get V equals 118 grams divided by 1 gram divided by milliliter. So that'll be volume equals 118 grams cancel out, milliliter. Now, over here, we're gonna do this. Milliliters to fluid ounce. We know we have 118, and there you can see it's 3.99. Amazing! The water gun is advertised for 3.72 fluid ounces, and we actually didn't need to convert it because it says 110 milliliters also. So there's an additional 8 milliliters that we found usable in the water gun, which is good. So now we shall test the next concept of the distance. Alright.
Okay, so this box claims that it could shoot up to 15 feet, but relating velocity and distance is a Physics 1 concept, so we're going to relate pressure and distance because it's a Physics 2 concept.
Okay, 6 centimeters. Fire shot. Another one. So in order to use Bernoulli's equation, we need to find a velocity. Now velocity can be found by setting distance x is equal to velocity times time. We know the distance to be 45 inches as in our experiment, and that converts to 1.143 meters. So 1.143 is equal to velocity times time. Now, it's really hard to measure time because we don't have a stopwatch, and we're solving for velocity, so we can find time using the formula height is equal to negative 1/2 gravity t squared times squared. We know the height to be 6 centimeters, which is 0.06 meters. And now we can solve for time. T is equal to 0.1106 seconds. And we get a velocity of 10.334 meters per second. Now that we have velocity calculated, we can plug it into Bernoulli's equation to find the pressure within the water gun. This side will represent the initial conditions of the water gun, and this will represent the conditions of the water outside of the water gun. So inside the water gun, velocity is 0, so all of these will become 0. We're going to have the rho gravity height plus the pressure inside the water gun. This is what we want to solve for. Since rho GH is the same on both sides, we can cancel it out as seen here, and we're going to get 1/2 rho, which is the density of water, times the velocity final, and pressure of the atmosphere, since it's pressure outside the water gun. So figuring that out, we get pressure 1 is equal to 1/2 times 1,000 kilograms divided by meters cubed times 10.334 squared plus pressure atmosphere. Now pressure atmosphere is 1.01 times 10 to the 5th and divided by m squared. So we can find out that pressure 1 is equal to 1.54 times 10 to the 5th newtons divided by meters squared.
First claim, we didn't really need to use any sources because we knew density equals mass over volume, so we just calculated volume from that equation. But for the second claim, we used teachengineering.org, and it provided us an experiment to find the pressure of the water gun. Okay, bye.